Okay, welcome back to microeconomics. So this is where we stopped last week, right? After we derived the total cost function from the solution of the cost minimization problem. One thing to remember here is we went all the way to this cost function, and it calculate the minimum cost. So any cost that calculated out of this function given the input prices and certain quantities is already the minimum cost possible for this set of parameter. Keep that in mind. So it's not any cost but minimum cost. Now we also will have two other cost functions. The first thing is the average cost function, denoted AC, average cost. Easy now, which is derived by dividing the total cost function for the quantity, the output quantity Q. Now, all right. And the second is the marginal cost function. So the marginal cost function is calculated by taking the derivative of the total cost function with respect to Q, right? So it tells you how much extra cost will be incurred when you produce an extra unit of output, right? So let's look at some properties of the cost functions. We will not prove it here. By now, they must be very, very familiar to you already, I trust, and I'm sure that you could easily prove it by yourself. The first property is the homogeneity. So all cost functions, all proper cost functions are homogeneous of degree 1 in input prices. So if you multiply or you increase all input prices by the same factor T, for example, in case of inflation, the cost level or the cost curve will also be shifted by a proportion T. This we learned about a homogeneous function already now. The second property is non-decreasing in Q, B, and W. Even though this sounds very obvious, right? Super straightforward. If you produce something, you increase the price of the input price or increase the quantity, then your cost should not be decreasing. No. However, let's not take it for granted right now and go back a bit to our cost minimization problem, looking at it from the cost minimizing perspective. So our starting point was we wanted to find some sort of input quantity to produce certain level of production given input prices in order to minimize cost. Now, imagine after you arrive in that and you arrive in a cost function, and then suddenly you find out you could achieve less cost by producing more. Then there must be something wrong, right? Because then that means that you was not minimizing your cost. Similar thing for input prices. If there is a lower cost for given higher input prices, then obviously you were not minimizing your cost in the first place. So you have to go back to your Lagrange setup and check step by step to see what's wrong. Now, so if you find decreasing cost in these arguments, then it's a contradiction to your model setup. The last property is the concavity. So cost function concave in input prices. Here I have to remind you a little bit. So concave or convex or something is always a relative term. So it can be concave in input prices, but convex in output level, for example. So when we talk about, or when you hear about concavity or convexity, then make sure that you know what is concave in or convex in. Yeah? So here, cost function concave in input prices. And it says that the costs are lower when firms adjust to changing prices than if they do not adjust their behavior. How does that mean? It's not so obvious than the former two properties, right? But I show you. Here is what it means for concavity in input price. So suppose we are producing Q1 with input labor price W1 in a cost minimizing manner. So we have already a cost function over here now. And with this input price, we have this cost. Now. So now imagine that we're not allowed to adjust our input mix. Everything fixed and W increase. What happens? As I said, we're not allowed to adjust input mix. Let's go back to the definition of cost. In our case, KV plus LW, right? We're not allowed to change K and L. We also we're not allowed, but here V also remain constant. Only W change. So in this case, C is linear, and that's what you see on the graph here. The C passive is linear. Passive in a way that we don't adjust our input combination. Okay? So that's why C passive is linear. Cost will increase proportionally to input price. However, remember, our starting point with cost minimization is where we wanted to find an input combination in order to help us to minimize the cost of production a certain quantity, right? So it should not be the case that we don't adjust our input mix. And if we can adjust that, the cost should not increase proportionally, but should, in theory, lower than that. And that is where concavity comes in, because one important feature of concave function is it always lies below its tangent line, and the tangent line in this case is the C passive. Now, like what I told you last week with the example of the harvester for maize and rapeseed, right? When the price of capital on the harvester was increasing, now I could adjust my input mix by using more labor and reduce capital. Instead, I rent out the harvester to the neighbor in order to minimize the opportunity cost of using the capital input. And that is what actually happening here with the concave cost function. Let's revisit a bit about input substitution, which I know we have talked about that a lot last week, but still there's some interesting aspect coming out of the cost minimization over here. So we said about that change in the price of input will lead to the change in the input mix that the firm would like to use. So it is formalized by the change in K over L, the ratio of input, right? In response to a change in the ratio of price, W over V, while holding the output quantity constant. And this is defined by the derivative of the input ratio with respect to the price ratio of input. Does it look familiar to you? Now, if you remember, last time, one of the implication of the first order condition of the cost minimization is at the cost minimizing point, we have RTS, the marginal rate of technical substitution, L for K, equals MPL over MPK equal W over V, right? So at this optimum point, the W over V here is equivalent to the RTS. So if you substitute this RTS inside here again, you have the elasticity of substitution, right? So that's the idea over here. Still, we could denote it as sigma, and we plug the definition of elasticity in here, like last time, but now only replace the RTS with the price ratio. And this is an alternative definition of the elasticity of substitution. So in the two input cases, sigma must be non-negative, right? Because when W over V increases, that means labor price is more expensive relatively to capital price. Then the firm will use more capital because now it's cheaper to use more capital and use less labor, right? So in that case, the denominator, so W over V increases, and then K over L will also increase. That's why it's non-negative. A large values, so meaning the input use change dramatically when input prices change. And form adjusts very strongly to this price change. Now, however, one thing to note is this elasticity of substitution now only measured at the optimum point, because only at the optimum point, only because of the first order condition of the cost minimizing, we have the RTS equal W over V. All other points along the isosequence except this point that will not hold. Now, that is one thing to keep in mind. We could only do that at the cost minimizing point with the assumption that form minimizing is cost. Now, the convenience of using this definition or this term instead of the definition that we had last week is because empirically it's easier to observe. So in practical situation, of course, it's easier for us to observe the input use quantity and also the price of the input rather than the RTS, which required very closely examining of the technology that firm use to produce the output. Sorry. Here again we have the Schaeffer's lemma. Does it sound familiar to you? I hope still, yes. Now, so we talk about it when we learned about expenditure minimization. So here is exactly the same approach, just for the production counterpart. Now, so by Schaeffer's lemma, we could find the contingent input demand functions by differentiating the total cost function with respect to input price. Okay, so if you don't remember clearly anymore, go back to the week where we talk about expenditure minimization and look at it again. There's also another aspect which is interesting, is how to interpret the Lagrange multiplier, the lambda, which we introduced in our constraint minimization problem. I show you on the board. Okay, so now I show you how to interpret the lambda from the cost minimization solution. So this is what we have met also before when we did utility maximization and expenditure minimization. After solving for the solution of the minimization problem, here we arrived in the optimum K and L star, which is, let's say, as function of V, W, and Q. Now, Q0, for example, and L the same. All right. And using these functions, we plug it back to the original objective function or the Lagrange, then we get an indirect Lagrange or indirect objective function. And the indirect objective function in this case is the cost function. Keep that in mind. So this is what we get. With the lambda, also a function of input prices and output quantity. And from the first order condition that we have used to arrive in the solution for K star and L star, we also know that V minus lambda times MPK, the marginal productivity of capital, equals 0. This is the first order condition. Simply take the derivative of the Lagrange with respect to K. Still remember. And in the second term you have lambda times the derivative of F with respect to K. That is the MPK. Okay. Now I could also write it as V equal lambda times MPK, and I call it first equation. The second thing, similar, W equal lambda times MPL. We need it later. Alright? Now, one thing I would like you to know before is we first take derivative of the constraint with respect to Q0. Let's see what happened. This is the constraint now. So you will have d Q0 with respect to itself minus df k star L star with respect to Q0 equals 0, right? Because the constraint is 0. So now the derivative of Q0 with respect to itself is 1, right? And I can already put the other term to the right hand side. And think about it. How do we do that? Because f is function of k and l, but k star and l star now function of Q0 also. So that is the chain rule of two variables, right? What does the chain rule say? That says that first you take the derivative of f with respect to k star. And in times the derivative of k star with respect to q, right? Plus the equivalent for the L star. So that is partial derivative of f with respect to L star times partial derivative of k, L star with respect to Q0. Sorry, 0 is missing. Okay. And here we could already write that the partial derivative of f with respect to k star is nothing else than the MPK, right? Times plus again MPL times the partial derivative L star with respect to Q0. Now, I want you to keep this in mind because we need it later. I could draw a square box, but I think it's nicer, more natural that way. Okay. Let's denote this as equation 3. Now, go back. Take derivative of C W V Q0 with respect to Q0. We would have Q equals. Now what is C? By construction, this is C. This is what we did last week, right? So this is C V doesn't work well. So this is C V W Q. Now, so we use this here. So that means we have V times the derivative of K star with respect to Q0, right? Because K star is now a function of Q0. Similar, W times the derivative of L star with respect to Q0. And now, the next thing we could do is we substitute 1 and 2, V and W, which we have prepared with equation 1 and 2, into this derivative. So, because of 1 and 2, we have Q0 equals V is lambda times MPK, right? Times the derivative of K star with respect to Q0 plus lambda times MPL times the derivative of L star with respect to Q0. Now, and we could already factor out the lambda. So inside we still have MPK times derivative of K star with respect to Q plus MPL times derivative of L with respect to Q0, right? And because of the result over here from the derivative of the the constraint, we would have this whole term in the brackets equal 1, right? So this is 1. Now, therefore, we have, because of free, the derivative of the cost function with respect to Q0 equal lambda times 1, which is lambda, right? And if you still have an impression last time when we talked about the utility maximization, if you take the derivative of Lagrange with respect to Q0, you also have the lambda. So, with respect to Q0. Therefore, up to this point, it should be clear that the lambda can be interpreted as marginal cost of output. So that is, the cost will be incurred when you want to produce a little bit more, like a small amount more of output quantity Q0. And that's how we understand the lambda.